Ladies and gentlemen, boys and girls, friends and guys, gentlemen and frenemies. Lovely to see all of you. Welcome back to a Gabversity, where facts care not about your feelings. It is probably very early for most of you around the world, and we've missed our people from Israel. It's been a little while since I've seen you. And we have Abyss. Abyss is up early for some bizarre reason, but it's lovely to see you, my friend. So we're going to start simple, talk about a two-particle system. Hey, Mr. Abyss. And let us begin. So we remember that first of all, sleepless night. I'm sorry to hear that. Well, this will send you to sleep, maybe. Mega. Hello, Mega. Okay, so what are we talking about? First of all, we did one-dimensional equations. Then we did two-dimensional equations, which was one space and one time. Then we did three-dimensional equations, which were the spheres. And then we did four-dimensional, which was the spheres. I hope not. The spheres and time. So it was a four-dimensional object. Now we're going to go up into 7 and 10 and 13 dimensions. But what that happened in this universe, what they look like is multiple particles on the same or very similar wave function, or a collective wave function. So it's very interesting. You can think of the universe as many particles, or you could think of it as one particle going through a huge amount of dimensions and a lot of them overlapping to make it look like there's multiple particles. Both of those sort of work, I guess, at least without too much scrutiny. All right, so let's get cracking, Mr. Abyss and family. So if you guys remember, I'm going to draw the maths for you. If we remember, we have the wave function. And it's a bit blurry, I'm sorry. We'll try and fix that. Come on, there we go. So we have the wave function, and the four-dimensional one was R. And R was 3 dimensions of space and time. And now the two-particle system, that's for one particle. Okay. Hey, Goodman. Now, for two particles, we're going to have the wave function, and it's made up of, this time, R1, which is 3 dimensions on its own, R2, which is 3 dimensions on its own, and time. So there you go. This is now a much bigger wave. All right. Now, still, we are going to look at the evolution of this wave via the Schrödinger equation. This does not change, which is I, the two-dimensional number. Here, the Planck's constant, sliver, I call it the reduced H constant, are these tensors. Yes, you could say they're more complicated versions of tensors. Yes, absolutely. And then, but it's exactly the same phenomenon. So yes, d of the wave function with respect to time, okay, equals the Hamiltonian, which is total energy of the system, by the wave itself. All right, so the total energy of the system times the wave is the same as saying I, H, right, the reduced pixel size of the universe, the sliver, reduced pixel size, right, by the derivative of the wave over time. So you could sort of call it like the speed of the wave in a way, or how the wave propagates through time, right? Multiplied by that is the same as the total energy of the system multiplied by that. And this wave is made up of, you could call them, it's not exactly correct, but you could say that it's analogous to 3 tensors. You could say that if you like. You could call that, say, like a 3D tensor and a 1D, I guess you could say that. Yeah, roughly the same. It's the same concept, yes, sorry. I like to complicate things. Okay, now we remember, if everyone remembers, the total energy. I'm killing this. I'm killing a dead horse. All right, total energy of the system, right, is negative, and then reduced pixel size squared. So reduced h bar squared. Sorry, reduced h, or Jesus, h bar squared. Okay, over 2 by the first mass, so the mass of the first particle, by the triple derivative, which is the 3-dimensional derivative, which Abyss correctly associated with the upside down, aka reduced Planck's constant. Exactly correct, my friend. Minus h bar squared over 2 mass 2, okay, and then the second derivative, sorry, the second derivative in 3 dimensions again, okay, squared. Okay, so if you remember, initially it used to be just that on its own, right, plus the potential energy, but now it's going to be that and that. Okay, so we've got the 2 particles now in the same equation plus the potential energy of the whole system, which is the first vector, the 3-dimensional vector, excuse me, R1, and then the second 3-dimensional vector, R2, and time. For those who don't know, obviously I have this here because that's a vector, which means it's multi-dimensional, right? Where this here, it's a 1-dimensional time. We haven't gone into multi-parallel universes yet. Okay, and here, right, is, if anyone remembers, okay, this is how it looks. The statistical interpretation of the wave function squared. So here is the wave function, and that's R1, R2, and time, and then we make these 3D. Okay, and what we do is we say that if the normal of that squared, okay, in other words, right, if you guys remember, it is this multiplied by its conjugate squared, okay, and then d cubed R1 d cubed R2. So we're talking a massive integral here, right? If we're actually going to do this, hey, thank you for the hearts. All right, so when we look for the particle, if you guys remember, we always have to normalize the wave function and set it to 1. In other words, when we integrate over that section from minus infinity to infinity, we are going to find a particle. Obviously, we've said that from the beginning. Quantum mechanics, that is like the #1 thing we have to remember. Cyanide, long time. Cyanide in abyss, hello. Hello, darlings. Triple integral, if I'm not mistaken. And it's actually, yes, you are right, and it's a triple integral. So we have to integrate 3 times with respect to the first R and 3 with respect to the second. Hey, cyanide. Your shirt went in the post today, finally. Oh, man, I feel sorry for anyone invited to this one, because this one has the most complicated calculus. Unless you've done a maths degree. Here comes everyone. They're going to go crazy. We're all up. What are you all doing up early, you crazy bastards? All right. Hey, everyone loves sine. Isn't that nice? I like that. All right. So we have here the integral, right, of this thing. I love the reactions. I'm up late. My quantum on. Yeah, get your quantum on, imitator. That's a pretty cool name, imitator. Good play on words. I like a good play on words. 1, R2, and time, if anyone remembers. That's what we just did. So that's the first particle. The answer is 42. I would laugh if the answer actually comes up as 42. Oh my god. All right, and it's the normalized of that squared d cubed R1 d cubed R2 equals 1. Work inside to outside. That is exactly right. From inside to outside. You work them all around, up and down, inside and out. Okay. Heeg. Interesting names. All right, so here you go. We are squaring this 7-dimensional wave function. And we're going to do a triple integral. Yeah, this is just nuts. If you actually see how we'd actually do the maths of this, which I'm not going to do. This is now the concept first. All right, so that equals 1. In other words, we will find both these particles. Implosion. My friends, we are going to find both of these particles on this wave function. That is what we're saying, and that's why it's equal to 1, because it's 1 is 100% chance of finding both of those particles on that wave function. And why? Because it's actually a 7-dimensional wave function, which is 2 3-dimensional spheres that are locked together in the 4th dimension. He's absolutely great. You, my friend, are too sweet. The beauty is in the eye of the beholder, in this case, cyanide. Who's Gab? Yeah, hands off my Gab. Yeah, you can go to YouTube and go to Gab Smacked, and you'll hear about the things I can do, which are quite unique. Which is just clicked on it and I saw quantum and leaped. That is another good joke. You're a bit of a pun, the sexy Aussie genius you're looking at. Where is he? What? All right, my ego is getting too much. I'm going to go back. All right, so here, right, we're going to now get the whole wave equation. My God, my Instagram, now people are watching my videos 20 times at least. This is crazy. I'm almost at 1% of cyanide. I am honored. All right, so now, of course, you'll find a particle union go over the entire wave function, probability function. Damn straight. Oh, I love it when Abyss comes on. It's minutes since I do. This lecture is going downhill fast. I love it. All right. So thank goodness. Alrighty, so here is the 7-dimensional wave function. Alright, and time. Alright, and what we're saying is that equals the 6-dimensional wave function multiplied by the 7th dimension being time. So that is R1, R2 multiplied by e to the minus I, which is the interdimensional number, by energy, by time, over reduced Planck's constant, d2. You're probably ahead of me, my dear. All right, so this now is this. That's 3 dimensions. That's 3 dimensions. Together it's 6, but we overlap these 3 on these 3. So what's very interesting, this part is quite amazing. When you get to this level in quantum mechanics, you realize that mathematically, 2 particles in 3 dimensions is mathematically, what's the word? No different. That's not the word I wanted, but it's no different from 1 particle in 6 dimensions. And there's my thumb. 6. Hold on a sec. 6 dimensions. Right? 1 particle in 6 dimensions is the same mathematically as having 2 particles in 3 dimensions. It's phenomenal stuff, so it just goes to show you. So they just overlap. You put them over the same time, and then it looks like you have 2 particles, when really it's 1 particle overlapping on itself. Anyway, Wendy woohoo. That sounds like a martial arts move. All right, so now the total energy of the system. Let's get it. You ready? Total energy of the system is this, E, and that comes from up here. This E up here is right here, okay? And that equals minus h bar squared, which is the pixel size of the universe squared, over 2 by the first mass, multiplied by the second derivative, right, of the first 3-dimensional particle, minus, same deal, h squared over 2 by the second mass, multiplied by the second derivative of the second 3rd-dimensional particle, plus the potential energy of the system, which will actually be like this, R1 and R2. Now, there is probably time in there, but if we take a snapshot, then the time will become 0. All right, so there you go. These are the same equations we did initially. So the only difference is they're now just getting longer because there's more dimensions included. So that, right, that's 3 dimensions, where that used to be 1. That used to just be dx, dt, or whatever. Or, you know, the derivative of the wave function with respect to x, right? And now there's x, y, and z in here of the first particle, x, y, and z in the second part of the second particle, and that's the second particle, that's the first particle. So that's 2 particles now in the same system, obviously, because if we want the energy of 2 particles, then clearly we want to have the energy of both particles in the system. I mean, it's like saying if you want the energy of the milk and the chocolate, you get the energy of the milk and the energy of the chocolate, and you get the energy of the chocolate milk. How does that work? Oh my goodness. All right, so now let us go to the first question. 5.2. Let us see if we can apply any of this knowledge, because that was a bit abstract. So now, okay. The gradient inverted delta is formerly called the divergence, by the way, I just remembered. Ah, it is called the divergence. My God, that brings back memories. The divergence of f, yes, back from calculus days. Can I get the energy of the Red Bull? My dear, I think yes. Do you want me to leave? Do you want me to turn off the scope? Okay. All right. So let us try this question. Here is our problem. Our problem is, if cyanide drinks all the Red Bull, how much energy is left for the chocolate milk? Well, it's Eagle. Are you ready? All right, here we go. The motion of the nucleus in hydrogen by simply replacing the electron mass with the reduced mass. Yeah. All right, so find the percentage error in the binding energy of hydrogen introduced by our use of mass instead of mu. All right, so what we're going to do now is, this is now nuclear physics, right? And there's a slight error, so let's jump into it. Let me show you. Okay. The good thing about, as I said, you can split the two-particle system into two one-particle systems. That might sound simple, but it's ridiculous that that can happen. That's like saying that I can split this whole conversation into, I don't know, like my hey, super hard, awesome. I don't even think we can cash in on those in Australia, but still, I'm honored. I don't know, I've got to think of something. Like, I don't know, I can't think of something right now. Like A and bis. Like, you know, imagine I'm talking to A and then later I'm talking to bis, and then we put it together and I'm talking to A bis, right? That's a really bad example. I'll come up with a better one later. All right. So now what we're going to do is we're going to rip apart this equation to have a look at what's happening with hydrogen at a quantum level, okay? So let's have a look. We have positive and one negative particle. The binding energy of the electron in hydrogen in various energy states and the corresponding spectrum with the electron undergoes the transition states with what the energy levels are. If we use the unadorned electron mass, okay, we have, in the separation of variable solution, we get one equation representing a free particle at the center of mass and the other representing a single particle with the reduced mass of the system in the standard Coulomb potential. If we want to replace m by the reduced mass, we'll need the mass of the electron and the proton. Okay, so what we do is, you're teaching quantum mechanics and bashing snowflakes and trolls simultaneously. It's a lot of fun. Well, I couldn't do it without you guys. Could not do it without you guys. Too much fun. All right. So what's interesting, this is the part that's phenomenal in this equation, right? With the hydrogen atom, what you can do is you can look at what's happening to the proton and what's happening to the electron as if they're two different things, that they're not even part of the same freaking atom, right? Mum, you went to grab for the printer and I had to pull the camera down. Sorry. All right, my fault. I'm gonna cop it later. It's too funny. All right, the mum bomb. Yeah, it is a very bizarre concept. Hi, Gab's mum. Everyone says hello, Gab's mum. All right. So it's like, okay, I think I have a better solution. All right. Cyanide walks into the room and takes a Red Bull. Now I could, Eddie Looping, what are you doing up? I know it's 7:30. Yeah. So, right. So, hey, Helen, hello. So cyanide walks into the room to get a Red Bull, right? You saw my mum. Now I'm gonna have to delete this scope now. There's like a fraction of a second shot of some blurry person in the background. Yeah, I know. All right. So, what we can do, Queensland, same time. Yes, yeah. Sorry, it took me a while. Is we could say that cyanide's legs walked into the room and calculate the energy of the system of her legs, and then find the energy of the system of her upper body, and then put them together later and say it all happened at the same time. But we could also say it happened at different times. That's the weird thing about quantum particles. You could say that hydrogen is doing something, or you could say that the atom and the electron are both doing two completely different things, and then you add them up later. It's a very strange concept. All right, so here is the energy of the system. Okay, energy equals, and we're going to just say the ground state, so it's not excited. Hey, it's boring yet. It hasn't drunk the Red Bull, so it's not yet excited. So energy equals minus 1 over n squared okay, which is the energy level of the system. So before Cyanide grabs the Red Bull, she's still relaxed like Abyss with his relaxed photo there, right? So it'll be E1 equals the mass of the electron by our magic number E, which is just a constant to the fourth, over 2 times the Planck's constant squared reduced, right? Multiplied by 4 pi epsilon naught, which has to do with being relaxed in a vacuum, squared. Alrighty? So now we're going to rip it apart. So we've got the mass of the proton, which is 167 with 26 zeros in front of it kilograms. Mass of the electron, which is 911 kilograms with 30 zeros in front of it. And then what we're going to do is we're going to pretend that the mass is made up of the electron and proton. Now, Newton's law of center of gravity is this. It's very simple maths, this one. Mass of the electron times the mass of the proton over mass of the electron plus mass of the proton. And that gives you the whole mass, which is that right there. So you can see that basically the proton does nothing. The electron does nothing, sorry. It weighs almost nothing compared to the proton. Like, we're talking nothing. We're talking like 1/10,000th. All right. So we find the percentage error is 0.05443%, right? So if we look at the mass as a whole thing compared to actually looking at the individual parts, we actually get an error of 0.05443%. Now that's really important. Why? Because that error is how people were able to use Einsteinian and quantum mechanics. Believe it or not. Okay. Ah, you're a werewolf. Hey, hey. All right. Well, I will imagine the howling for 5 seconds before I can move on. All the best. Have fun. All right. It's important, and I think Abyss knows exactly why this is important. Because that little error is enough to convert the energy into an atomic bomb. Okay, so that was able to be used, that tiny bit of energy, because we know that E equals mc squared. So you only need a little bit of binding energy to be released, and you will create a nuclear bomb that can destroy the world. It's pretty crazy. Okay. Now we look at the deuterium atom. Okay. Rydberg constants for hydrogen and deuterium are. Okay, the wavelength produced by transition between states with primary quantum numbers n, I, and nf is for hydrogen between states 3 and 2. Okay, so this is quite interesting. We get a wavelength release for hydrogen from when you go from the higher energy state, Captain Deltron, the higher energy state to the lower energy state. All right, I'm not going to show you the maths in this one. Okay, we get, because it's not really useful for later on, unless you want to go make a nuclear bomb, which I don't advise doing. But you know what was really funny? I heard the other day. This is just on the side note. There was some white supremacist or something or other, which I thought was really funny because it was the Jews who ran away from Nazi Germany that came to America, which was the reason Americans were able to develop the nuclear bomb in the first place. I just thought that was quite hilarious. Okay. So the energy released in hydrogen when dropping down from the third excited state to the second excited state, for example, is 6,566.9 meters with 10 zeros in front of it. You have an eBay account in North Korea? My God, that is some serious skill. I don't want to know how that happened. All right, and for deuterium, it's 6565.1 by 10 to the minus 10. That explains why America wants to shut you down. All right, so 6565.1 by 10 to the minus 10. So basically, we're going to go 10 decimal places this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that would be 6 zeros in front of this thing, meters. Okay, so the spectral line difference is going to be that, because all it is this minus this. So in other words, you can tell if you're running with heavy water or with regular hydrogen, because the spectral line actually has a gap in it. Now, a lot of people who study chemistry do spectral lines, but they don't talk about the quantum mechanics, obviously, because that's not that department. But now you know it happens because of the wave function itself. The wave function can only exist for each atom at a specific energy level. Otherwise, it does not exist, at least in this universe. And so that quantized energy difference happens to be 1.8 by 10 to the minus 10. It's so small, but it's enough that you can read if a star even, for example, is giving off deuterium or hydrogen, regular hydrogen or an isotope. It's just, I love that stuff. Okay. Now, here's the next thing. What we can do here, we can make a weird, it's not antimatter, spectroscopy is awesome. I noticed you were pretty advanced with that when we were doing that in astronomy, yeah. All right, so if we pair an electron with a positron, okay, so a positron is the anti-version of the electron, right? Which has the same mass as the electron but a positive charge, okay? So it's like antimatter of the electron, right? In this case, the reduced mass, okay, the binding energy would be half of ordinary hydrogen, which is pretty awesome. Finally, we can pair a proton with a muon, which has a mass of 206.5 times the mass of an electron. That is crazy, because basically it looks like hydrogen, but instead of an electron, you've got a muon, which is massively heavy compared to the electron. So it's a weird-ass mutated version of hydrogen. And the mass of that is gigantic. The mass is 1692 by 10 to the minus 31 instead of 91069. Why is that 9? Oh yeah, it's 9. So instead of 9, it's 1692. And that's just crazy. Okay. So the Lyman A-line transition now becomes 6.5 by 10 to the minus 10. That's a massive difference. So instead of having 6,000, 10 to the minus 10. So that would be 656 nanometers. 600, let's say 656 nanometers. It's 65 nanometers. So it's unbelievably short. So that just shows you that the spectral line can get mutated. So just like you can mutate genetics, you can mutate the actual particles themselves. And once we can do that, we can start to build things out of new matter. Can you imagine that? I'm just starting to think, what could humans build? You know, they could build superhumans that were built out of this matter. I don't know. It's crazy. Crazy stuff. Anyway, that's all I got for today. The next one we're going to do in our next lecture maybe will be we're going to write down the Hamiltonian for two non-interacting identical particles. And then that might be too much mathematics. I think Abyss will be the only one who won't get bored. Maybe Captain Deltron as well, probably. Find the next two excited states. Yeah, I might do that in the next lecture. We'll see how we go. But that's it, my friends. Lovely to see everybody. Always a pleasure. And at Gabversity, facts don't care about your feelings.